And good afternoon, folks. So thank you for tuning in to another Risk Institute online session. Today, we're fortunate to have with us the wonderful Dr. Divya Persaud, who just finished her Viva a couple of weeks ago. So big congratulations to her. She's going to talk to us about her research on her thesis, exploring 3D imagery to support planetary exploration that she's been doing in collaboration with the Jet Propulsion Laboratory from NASA in the California Institute of Technology. So the presentation will be around 45 minutes with around 20 minutes for Q&A. Please could you make sure that your mics are muted, and if you'd like to leave any questions in the chat or raise your hand at the end of the talk, I'd be delighted to kind of select questions. So before we begin, I'd just like to make a few announcements. Our next talk will be our very own Mr. Enrique Morales-Dols on the 31st of May at 2 p.m. He's going to be talking to us about interval-based global sensitivity analysis for epistemic uncertainty. Following that, we haven't confirmed the titles yet, but we have Dr. Dalal Alajet, 6th of June from Imperial College, our alumni, Dr. Sylvia Tolo, on the 14th of June at 2 p.m, and Professor Dr. I'm not sure the professor actually, but Dr. Dominic Balog-Way, 21st of June at 2 p.m. So without further ado, let me introduce our speaker. So Dr. Divya M. Persaud is a planetary geologist fascinated by the stories of rocks in the solar system. As a postdoctoral scholar at the NASA Jet Propulsion Laboratory, she's working on missions to explore Jupiter's moons, Europa. Her past work includes her doctoral research using 3D imagery to investigate the exposed rock layers at the exploration site of Curiosity Rover in Gale Crater on Mars, as well as working to understand the geology of the icy moons of Saturn, Mercury, and asteroids and meteorites using satellite and laboratory data. She's also a poet, composer, and speaker, and has spoken and performed her cross-disciplinary work internationally. So very excited to welcome our speaker today. Really great topic and talk. So please, would you like to start sharing your slides? And can I also remind, there's a couple of people who have just signed in and their microphones aren't muted. So just remind those to mute themselves, please.
Great, thanks so much, Francis. Just gonna go ahead and share my screen. And yeah, thank you so much for having me here today. I'm really excited to talk to you about my doctoral work using 3D imagery to support particularly Mars exploration. So my background is geology, and the work that I do is a whole mix of things, but informed by planetary geology. And we can understand geology as investigating the story of a planet. Historically, that's meant our planet. And so I just have a couple photos on the left showing what geologists do in the field. We go out, we look at outcrops, meaning rocks exposed, and we take measurements, we draw, and we try to reconstruct that story. And so on the right, I have something called a stratigraphic column. And that's just an illustration capturing or summarizing the geology from an outcrop. And the idea is that we're trying to get back through time and understand the different environments that have existed just based on the rocks that we see in the analyses that we do. Planetary science isn't so straightforward because we can't send people except the moon. And our geologists in the sky, so to speak, are satellites. So there's just a little animation showing a Landsat 8 at Earth, and similar satellites in different places give us similar imagery. So we have Earth in the upper left. Here's a satellite image of Mars, and I'll talk about that loads today. This is a picture of Europa from the Galileo probe, which flew in the 80s and 90s. And so while those satellites are great, they have cameras, they have different types of sensors. They're not quite the same as putting something on the surface. And so rovers are our geologists on the ground. So this is a picture of Curiosity rover on the surface. I'll talk loads about Curiosity today. And this is a panorama in the background that Curiosity has taken with one of its cameras. It's loaded up with loads of cameras, loads of different instruments, a little chemistry laboratory, and it can do types of analyses like shoot lasers at rocks and get a an idea of what those rocks are made of. So it's not quite a geologist out in the field who can do little experiments, who can take samples back to the laboratory and look at them under a microscope, but it can nearly do those things and with our direction. The trouble with rovers is they're tiny and you also have to get them to the surface. Sorry about that link. And getting them there is not trivial. So while those rovers have these really nice local views, the best that we can do is use those satellite data to actually prepare for us to get there. And satellite imagery can give us both the scientific information that we need to select somewhere that's interesting based on what we're looking for, and also engineering information. So in the upper right is a slope map that was actually derived from 3D satellite imagery. And I'm going to be talking about 3D today a lot. And I'll tell you why in a second, but from this, so a slope map is derived from a 3D view of the surface where slopes can be calculated. And that's really important for thinking about navigating a really expensive, really fragile piece of technology on another planet. And then in this corner, there's a bit of a 3D perspective view of an image. Again, I'll explain all of this soon, that exposes some interesting different mineralogies. And so that's scientific information that we can use for, again, picking a landing site and also figuring out where to drive a rover. And all of that eventually leads us to having the rover landing successfully and getting the data that we'd like. So here are just some examples. This is Gale Crater, where Perseverance rover landed last February. So you can see this is where the landing location was. And while, so I don't have an example of satellite imagery helping Perseverance, but it was kind of unique in that it took images on the way down and then made decisions as it was landing. So it was kind of speeding up that little process in its onboard computer. So it was able to take a look at the surface changing in 3D as it descended and develop a hazard map. So basically red is bad. And so if you take a look at where Perseverance decided to land, it's quite incredible that that it did so really safely and also chose that spot. Here's a actual satellite image. So I'll talk about this camera soon. The HiRISE camera, which is in orbit around Mars, was actually turned to watch the landing of the rover. So this is kind of pushing the envelope of what in future we'll be capable of doing more and more. And it caught sight of little Perseverance rover with its parachute, which is pretty cool. With Curiosity rover, Curiosity has been on Mars for 10 years now. And so satellite imagery has helped with defining hazards, but also with localizing the rover or locating it. And I'll talk about why location matters in a moment as well. And also figuring out navigation. So in the lower right, we have the view from Curiosity at the top of this little cliff. And again, this is a satellite image being shown in 3D, and we can actually see that the rover is on the edge of this cliff. We can also look at the terrain that it's approaching as it's going this way. We can use that 3D imagery as we plan the next part of the traverse and combine that with mineralogy from different cameras. I won't talk too much about that today. So here's a perspective view of some 3D imagery with the rover traverse overlying it, and then these units that have been defined from different multispectral cameras to reveal different types of minerals. And that's important for nerds like me, geologists who want to investigate some of these mysterious mineralogies going forward. And that informs how we choose traverse. And also it's being used for thinking about the future steps of human exploration. So this is Aristarchus crater on the moon being visualized in 3D. And I stuck Earth back in there just because I think it's fantastic. And Aristarchus crater is considered a primary target for the Artemis program for humans landing for the NASA Human Exploration Program. And this is really important, trying to figure out what is scientifically useful and also especially what is safe for human beings. So I've talked a lot about 3D, but what are 3D images and how are they made? So if you think about how we sense in 3D, our brains get 3D information because we have two eyes, or we can think of it also as two ears. And it's the space between those things that matters. So if you imagine, if you hold up, say, a pen in front of you, and you look back and forth with your two eyes, they're inputting two different images into your brain. And your brain is taking its understanding of your environment, the angle of the sun around you, how shadows work, how color and lighting work, also your physical senses, and takes those two images and computes a solution for depth. So if you find that you cover an eye and try to walk a sort of perilous path, it's really hard to balance. That's because you're not getting the full depth information. You're just probably guessing it from shadows and such. Computers do much the same way. So if we think about image processing, the principles are the same. These image processing algorithms are based on how humans understand the world around us. So this is one technique for getting a 3D image called photogrammetry, and that is taking two images, which are called stereo images. We understand the satellite pointing at each of those spots. We understand its altitude, the angle of the sun, the angle of the satellite relative to the sun, and some other parameters. And we can give all that information to the brain, which is our processing algorithm. And it can take all of that information and calculate a solution. And the solution is a 3D image, which you can think of as it's just an image, but the brightness of the pixels tell you what the elevation is. And that product is called a digital terrain model, or a DTM. I'll try not to use too many acronyms today. So you'll see this repeating a lot in my presentation. This was the focus of my thesis. I selected it to do experimentation with 3D processing and also for science to complement Curiosity rover. So this is about 30 kilometers southwest of where Curiosity is about now. I'll talk about that in a moment. So if we think about 3D images of from satellite data going towards the end product, we want rover landing data. So we have the scientific information, the engineering information coming from the 3D satellite data. And what goes into that is the instrument geometry and 2D images. And the magic happens here with the image processing. So image processing is really important, even if you don't want to land a robot on another planet. If you want the scientific information, if you want to think about engineering in the future, those things are really important. So the data products to study geology, which is my focus, and also to process things in 3D, were Gale Crater, and that's the landing site of Curiosity rover. And my goal was to get these 3D images covering Gale Crater, which provide 3D information of geology. So if you take a look here, when visualize, these 3D images expose outcrops, they expose textures and things that we don't intuit from just the 2D. And then we want also the 2D images corresponding to those 3D data. And we want that because you might have that 3D sort of shape and map, but you can't necessarily interpret it just from that. You want the 2D information. And all of that can also be used in a big 2D base map. So if we're doing any sort of science, we want to make sure that we have a nice map that we can produce that other geologists can look at. And that can be mapped with other maps as well, including ones coming from the rover. One of the issues, or actually the main issue, is where. Where are things? So I mentioned where the rover is really important because we're driving it and we don't want to drive it off a cliff. We don't want it to drive into dunes and get stuck. So it's equally important that we know where the satellite images are. This might seem kind of trivial. It's not. Satellites are really precise. They tell us, they give us loads of information with every single bit of data that they send back. They say everything from the longitude and latitude to the altitude above the surface, to the temperature of the sensors, to the relative location of the satellite versus numerous objects in the solar system. But when you want precision, it isn't necessarily correct. And when you make 3D models, those errors can propagate. The reason we need to know where things are is that we want our data in a consistent spatial framework. For doing our science, if we want to make, say, a big base map over an area, we want to make sure everything's in the right place. We don't want these weird overlaps. For engineering, if you're driving a rover, you need to know where things are if you're trying to map out a traverse. And reproducibility, which is really important. I want to be able to pass my map on to other people. They can drop their data products in and everything is in the right place. We're not seeing a 200-meter shift between things. The way we do that is we look at the ground truth that we have. For Mars, we're really lucky. We have this, we had this instrument called the Mars Orbiter Laser Altimeter. This was a laser in orbit around Mars on a spacecraft, and it shot these pulses down to the surface, measured the time for return, and extracted elevation data. So on the right, you can see the global product from that instrument, where color denotes elevation, and it was pretty precise. It gave 463 meter per pixel coverage of the entire globe within about, I think, 10 centimeters precision. It's a pretty incredible instrument. So that's the best ground truth we have of where things are. The trouble is, if you think about MOLA being 463 meters per pixel, which sounds, it depends what industry you're coming from, but it is global, which is amazing. When you look at the cameras that we have at Mars, they range from 4 meters per pixel up to maybe 12.5 to sometimes 50 meters per pixel, all the way down to 25 centimeters, which is our best. And when you make them into 3D, they lose some of that resolution. Talking about one meter to about 30 meters, which is massively different from this. And I'll give you an example. So if we look back at that feature that I showed before, that big canyon, that's the focus of my thesis. This is what it looks like in MOLA. And it has this sort of grid. There's not any information I'm getting from this. You look at it in CTX, which is 18 meters per pixel. These are 3D maps, by the way. So again, color is showing elevation. And here's high-rise overlaying it. High-rise is the best that we have. That's 1 meter per pixel. And there's loads of this incredible, beautiful texture. And if you want to compare these two things, it's really, really hard. So how do we know where things are? So there's a method from Tao et al. 2018 of trying to use this cascade of multi-resolution images that we have. So I explained the different cameras that we have orbiting Mars. So say we look at Gale Crater with all of them and make 3D products at their different resolutions. And at the base, we have MOLA, which is 463 meters. And if we go progressively by resolution, so the next lowest, which is 30 meters, the next lowest, which is 18, until finally we get to the highest resolution, which is 1 meter. It's a lot better than trying to align this really sharp image to this really fuzzy one. So that is all explained in this paper, the sort of gains from doing that. So my work involved processing these top 3 digital terrain models. So HRSC, which is the high resolution stereo camera, and also context camera, I did myself. And then this one I sourced from the University of Arizona from the instrument team, and also did some processing there. And I won't get into the processing today because that is a very deep rabbit hole. But I'm going to talk a little bit about this problem of where. So again, just explaining this cascade again, HRSC is intrinsically aligned to MOLA, which is great. DLR was amazing when they built this instrument and deployed it, that every single image, we actually do know where it is, and that's been validated. So my work was processing these terrain models and then aligning them. So I wanted to align CTX to HRSC, which is shown here, and then high-rise to CTX. So we start with MOLA, HRSC is on top, then CTX, then high-rise. And then I compared each of them to other published data to do quality analysis. If you see a little shift between HRSC and CTX, that's HRSC and MOLA in the background, that's artificial. I don't know why that was happening, but I made this yesterday. So here's just an example. Again, I won't go through these detailed comparisons, but this is one method of evaluating the quality of the CTX product. So basically, I plugged in the CTX images into the little algorithm. It spat out a digital terrain model. I wish it was that easy. It wasn't. On the left, you have the HRSC that I'm comparing to. And then on the right are these two CTX products. One is from the Natural History Museum, who had published similar data. And then this is mine. And so what I did was I used these automated algorithms. What the NHM did was use a semi-manual method to do image matching. And the differences kind of become subjective. So the NHM one is definitely crisper along these little features here. I hope you can see that, and as well in this box. And you sort of see them that they're scalloped in mine and a lot less detailed. So one big product from this or lesson was that the automated method lost detail, but it was also automated. It took about probably 2 days to process this. I didn't have to touch it, didn't have to intervene after inputting parameters. But the semi-manual method is, of course, taxing to the person who does it. Also important is that I know that geologists process this. And I'm a geologist who processed this, and I had to go through all sorts of refinement to improve what this looked like. So it kind of ended up being about who was using it at the end, who is looking at the terrain and thinking, I need this CRISPR, or I need this, I actually don't want to spend time fixing or refining this area. I didn't really care about this area myself. So the question became, is automation actually improving the quality that we get? If we know where things are, do I, as a geologist, really care about these features? Absolutely not. Do I care if I'm sort of showing someone and I'm saying I'm giving this talk and I'm saying my product is clearly inferior? Maybe. But it really depends on who's going to use it. It really depends on who's processing it. And that was a big lesson. Here's another way of comparing that I did. So this is showing that valley again, but this is in CTX. And I would take these profiles, and these profiles are topographic profiles, meaning that you draw a line and it samples the 3D data below. And here out in the real world, we might do that by surveys. We might actually go out and measure things. So this is really useful for a geologist to know, are the profiles similar enough? Compare them to HRSC, where kind of gets fuzzy. A lot of this is because CTX is a lot crisper than HRSC. And if you look at these two, you think, okay, they're pretty similar. It's really hard to quantify their dissimilarity. So you have to do these experiments kind of in tandem together. And it still comes down to, okay, what am I actually using it for? Am I someone who studies the shapes of canyons? No, I'm not. So I don't really entirely care if they're slightly different, but someone who actually studies these things is really important. So that became quickly apparent that you can do these quantitative and qualitative comparisons. I didn't really talk about quantitative today because that's described in Tao et al. 2018. But it became really apparent that it meant that I was definitely biasing what was considered valid as a data product, because I don't care about necessarily the shape of this. I do care that it doesn't have huge artifacts or any sort of missing data at the scale. I'll talk a little bit about that in a moment. So after you make your digital terrain models, you have your 3D data. I mentioned that they're not that intuitive to understand. You really need that 2D data draped on top of it. And I'll show you what visualization looks like soon, so get ready. But these 2D images are draped onto it, and that is called orthorectification. You can think of that as we've aligned these 3D models, and now we have these 2D images sitting over here. We need to drape them on, and that's kind of aligning the 2D image to the 3D image. We want everything exactly where we want it. and then it can be visualized and be useful and then be used as a base map. I won't talk too much about orthorectification. Again, that is a deep rabbit hole, but it's largely simple. It's automated using tools that are used by the community. So you take so your DTM, your 3D product has been produced by your left and right images, which give them camera model. So that's the pointing and the optics of the camera, the lighting conditions and everything go into the 3D model. And then what the software will do is take the 3D model, it'll take one of the images and all that information from both of them, especially the projection and the extent, which just tells you how the 3D globe is rendered in 2D. And then you get an ortho image or ORI. This is just the 2D image that's ready to be draped onto the 3D. And that's a pretty simple process. It will line up, but that gets complicated. So I'm going to show you, so the 2D, I'm just telling you, I won't show you, the 2D agrees with the 3D. And we know the 3D aligns with each other through these validation techniques. But when you compare the 2D from these two different cameras, so I'm showing you HiRISE and CTX. So CTX is 6 meters per pixel. HiRISE is 25 centimeters per pixel. They don't look great. They look like they're actually viewed at slightly different angles. Some of these layers are shifting around. Some of these features are shifting around. So if the 3D agrees and the 2D agrees with the 3D, but the 2Ds don't exist, you have this weird sort of mix of alignment problem between the 2D and the 3D, if you follow me. So clearly any sort of differences between, say, the 3D models or the 2D and the 3D, whatever it is, propagate across resolution. So you might say that, okay, the alignment looks great to my eye, and then suddenly when you are working with a higher resolution thing, it doesn't look so great. So this was a big result from my work, was that you can align everything as you want, following strict measures, and still when you plop them into the map, what does where become? If I'm trying to point to the little edge of this cliff right here, it moves a lot. I would say that is about 20 meters that it's moving. Someone might not care about that. As I mentioned, someone who's looking at this canyon as a whole, it's 2.5 kilometers across. They might think that makes no difference to me. If you're me and I'm looking at rock layers that are towards the meter scale, suddenly that matters a lot. So there are ways to refine these things, and I went looking. So you can do the semi-manual refinement. So you essentially pick pixels across two images, and then you pick an algorithm and it sort of forces them to agree. This isn't data I'll talk about today, but it's a nice colorful illustration of showing, say, this crater looks all sort of squat, and this one's nice and circular, and we'll get it to fit. So here's a sort of warpy version, and then there it is lining up nicely. And so this is a very human intensive way of doing this. And so it's involved, it's also subjective, it's also really hard to reproduce if you're trying to tell someone else how to do it, but it also gets you the results you want. And as many of you probably think about all the time, the results you want can really easily bias what you're doing. So how can we quantify or qualify the way this image has been shifted and apply that in future? You can't really. Me as a geologist, when I look at comparing these two images, and I use an extreme example because it was really difficult, I'm using geological sensibility to compare these two things. I'm looking at what I understand of the landforms that I'm seeing. I'm also looking at probably other papers about these features, and someone else is going to do this completely different from me. It might look the same from above, but if you go into detail, it might look very different. And so these biases start to creep into these alignments, and when you might think it's sort of trivial, but when you're thinking about this little 20 meter budge that's happening, it suddenly becomes really important if you're interested in things at that size. So I stuck my base map together. I had the orthorectified images, and then I did, I applied that semi-manual product to the region because I wanted this nice big base map to start mapping my geology. And they're in the right place. I forced them right, but you see sometimes they shift because they might agree with each other, but not adjacent images. They might necessarily, you see them shift, but when you zoom in, they agree. The base map here is actually from a different publisher. And so that was a different thing. They had aligned their images as well, and they were correct. So what does any of this mean? If things are shifting around by meters, and say this was a rover landing site, which thankfully it isn't, and you were trying to land on an edge, that becomes really important. That's a really huge concern. And so this started to emerge as I constructed this base map. So when we think about uncertainty with this image processing, I really want to be able to quantify in future how these things change, how they compare to each other. So probably through feature tracking, not just between those 2D images, but also the 2D and 3D, which I'll talk about in a moment, to quantify these differences and how these errors propagate, because it's really important. The truth of where becomes problematic, especially where we lack this ground truth at that resolution. MOLA is not going to help us when we're looking at 20 meters. It's going to help us when we're looking at a couple kilometers. So something that I sort of looked to think about these issues was a paper from a planetary geomorphologist, Victor Baker, who does this philosophical work around the concept of uberty. And uberty is this, it's just a word that means sort of serendipitous discovery. And he argues that in fluvial geomorphology, so when we're looking at ancient river systems on Mars, a lot of the times we as geologists, we have, or numerical modelers, we have these models. A lot of the time we end up tweaking parameters to get a certain result that resembles what we see on the surface, and then say, okay, those parameters are correct. So if you're looking at an ancient river system on Mars, and your end feature looks like a canyon, for example, on Mars, and your parameters are the climate at the time of formation, concluding that the climate, your estimation of climate from those parameters was therefore correct. He highlights that as almost a false logic, right? So we shouldn't be driven from the top-down modeling perspective, but rather empirical and observational science. And a lot of that means looking to Earth as an analog for what happens on other planets, largely Mars. So I just have two pictures here of a panorama from Curiosity rover and a little view of the Atacama Desert here on Earth. So understanding how, and he talks about how nature presents herself, of how these features actually form in environments where we can actually see them forming, where we have a historical record, and you can think of it as ground truth, in order to understand the climate that produced similar features. So rather than having your model telling you, or having your bias of interpreting your model telling you, you're being informed by empirical evidence out in the field. So I've been thinking about, what if we apply that to imaging, right? Because I've highlighted a lot of points of subjectivity when we do image processing. And we can think of these digital terrain models. Say we go back here, even just 2D images. When we look at these images, as a geologist who's an end user, who's probably just mapping geology, I look at this as a representation of the truth. I look at it and I think I know where things are, and the shapes and morphologies of things I trust. But what if we thought of images as models of the surface? So should we be thinking about what the image tells us rather than what we as geologists understand of surfaces? That gets very esoteric, but you can think of it as I combined this idea with a term drawing as from Janet Fratesi's book, Seeing Like a Rover. It's a really excellent book, which was an ethnography of a rover operations team, the Opportunity rover. And she basically sat in the room and looked at how scientists and engineers understood the surface and gleaned knowledge from what the rover saw. And she discusses how people make images based on what they need. So say I'm an engineer and I look at this image, and an engineer did look at this image and thought, okay, I need higher contrast on the stuff in the front. I need to think about the hazards for the rover wheels. I need to think about traversability, meaning how safe is it to traverse. I need to plot out an area of traversing that is smooth, that won't harm our technology. Whereas a geologist who definitely informed this image that we have here is looking at, okay, I want the color here. I want the contrast to be lower because I want to see the textures on these rocks here compared to the textures over here. I want to see some of the stuff in the background. And both of those images are correct, right? They're correct representations of the surface, because correct doesn't have a meaning suddenly, right? It depends who you are, what you're doing, and why. And she constructs that term from seeing as, which is from a paper from the 1970s. So you can think of the sort of classic duck rabbit image. You can see it as a rabbit, you can see it as a duck. You're not incorrect either way. It's up to your interpretation whether it is a duck or a rabbit. It suddenly becomes seeing something as something to it being something. And so she thinks of it as drawing as. So the person who drew this, did they draw it as a rabbit? Did they draw it as a duck? So if we combine those two ideas of thinking of images almost as models of the surface, especially 3D models, as these estimations of truth that we are just taking as a priori or as facts, combined with drawing as of what's actually important to the end user. And think about what empirical imaging is. It requires us to understand how we process images as end users, how we do these little alignments, and what geology we're actually going to do at the end. Or am I an engineer who's just looking to map hazards for a rover? Am I a geomorphologist looking at landforms that are 5 kilometers big? Am I a sedimentologist who's looking at little rocks that are about 4 meters across? If we think about it empirically, our images are going to look different. So this is something that I'm still thinking about. This was in my thesis and trying to think going forward what types of experiments we can do. So taking a pause from all of that, we have all of our 3D products. We have this high resolution data set over this canyon. And I'm going to walk you through some of the 3D visualization that I do. So I'm going to take a little tour. I've talked about Gale Crater and Curiosity rover kind of in passing, but it's time to actually look at this. This is a big CTX mosaic, so that is 18 meter per pixel terrain, and draped over that is 6 meter per pixel imagery. It's quite fantastic. This is about just about 200 kilometers across. I'm going to take you on a little tour. I rendered this myself. Most of the videos in this are mine, actually. So we're gonna look in perspective at Gale Crater. So right now I'm focusing on this central feature here, which is called Mount Sharp. Mount Sharp or Aeolus Mons is kind of unknown how it formed. So Gale Crater was formed by a big impact 4 billion years ago, and then over 2 billion years this thing formed. We don't know if it was volcanic, if it was sedimentary, if it was water delivered, forming this big mound in the middle. But we do know that this crater was filled with water. Maybe it was filled with ice. This feature has been having scientists scratch their heads for a while. It sort of looks like glaciers here. But the floor was a big lake. There were these massive canyons coming from the rim, filling the lake environment on the floor of this crater. Here's that canyon again. That was my focus, called Sicaria Vallis, where you can see, I'll do a close-up of this, so I won't talk about it too much. And here's the Curiosity rover traverse through about August 2020. So it went from these deposits here, which were Lake Delta deposits, through some of these active dunes now. So looking at loads of clays and sediments that reveal a lake environment that is slowly sort of drying up later in time, if we think of up as more recent. And so that's just a general tour of Gale Crater. As Curiosity rover is traversing upwards, it's approaching this boundary towards a very different chemistry. So it's going from sort of lake clays, groundwater altered minerals, and now into these sulfates. And we don't really know where they come from. And this is its opportunity to investigate this weird, mysterious feature in the middle of the crater. So if we think of, so I mentioned that Gale Crater was formed by a giant impact filled with water, flooding it from the region. It dried up, and then groundwater came through these cracks and altered chemicals. And then we don't know what's going on up here. We have the geology. If we think of this as like a little schematic of what the rover has done so far, it's allowed us to, I don't know why this is backwards, I'm sorry. Allowed us to reconstruct or summarize the geology in that area in a stratigraphic log, like I mentioned before, that we get to do here on Earth as geologists. As it's ascended, it's got to look at these different units. So now the question is, what's going to happen up here? Curiosity is not going to live forever. We're not going to get everything up here. And so I'm really interested in the geology that we can get from up here and how we can use 3D data to actually do that. So here's a close-up of that canyon, Sicaria Vallis. It really is amazing. It's about, at most, about 2 kilometers across. It's about 400 meters deep. It's an incredible just exposure of loads of these rock layers. Even if you don't know about geology, it's really cool. But basically, we're looking back in time. We're looking at most recent down to who knows when this was. These layers are exposed in 3D. You can actually see sort of the shape of them. You can see other features in the canyon that are interesting, like this thing on the floor that I won't talk about today. And then there are these layers here that sort of look repeated, which we kind of see in lake sediments when you have a lake or an ocean that is rising and falling, an elevation or periodic precipitation. So basically I processed this because I was interested in it, and then I looked at it in this 3D video basically, and I thought, wow, we could actually study these layers. We can treat this as an outcrop that I'm going out and measuring thanks to some handy software. The software that I use is called Pro3D. It was developed to support the Rosalind Franklin rover from the European Space Agency. It's also being used to support NASA activities. And so the upper left is the view. If we drop in that 3D data draped with the 2D data, it's like kind of like a field environment. You can go in, you can draw these lines, you can, so these little discs are measuring orientations of these layers in 3D. So I've gone through, I've identified these different units in this canyon and extracted that information. I've mapped it in 2D on that base map that I showed before. And from there, we can actually, I'll talk about that in a moment. Well, we can construct that little story that I was talking about, the stratigraphic log, and describe these units. It's not quite the same as going out in the field or having a rover there. But you are also getting 400 meters of an outcrop, which the rover can't do in one sitting, and a human can't do in one sitting. So it's pretty amazing. You can just basically rotate and play around with this 3D data. You can draw all over it. It gives you loads of quantitative information of what you're doing. And then you can construct the geologist story from that. So the 3D analysis looks like taking all those data, turning it into quantitative data on layer thickness, and also the inclination angle of these layers, which is called dip. Combining those data plus a map, you can extract outcrop models. So down here, I have something called a cross section. And that is basically that profile that I showed before. When you draw a profile going across a feature, I've drawn this profile, and then in 3D, I can actually get the represent the layer thicknesses and inclination angles. So this is just one example. This isn't published, so I haven't shared all of them, but I have 11 of these models. And you can look at how these layers change throughout the canyon, which is really important when we're trying to think of, okay, so what environment did these represent? If I'm looking at this in detail, sort of, was this a lake environment? Was this a dry process? Was this unknown? Was it volcanic sediments? And looking at these different types of trends, we can also see emerge that when these inclination angles, these dips change going through an outcrop, we get something called an unconformity. An unconformity is basically, so I've propagated some of these boundaries and you see this layer truncate. And that happens when you have a depositional process. Say you have a nice lake environment and it dries up and the sediments are there, and then you have erosion scooping out some of that material, and then you have new material going on top of it. It can also just mean a process stopped and then a different process took over. Here on Earth, it could mean that something was angled, it was tilted, there was tectonic motion between these two time periods, but basically it shows a change. It's in time. We don't know when this was, but it is interesting. It means that an environment was changed. And that was a major result of this work. And may point to evidence of water just with other observations that I made. Again, this isn't published. So again, here's this 3D view, here's the 2D view of the map that I've gotten. And here's a summary of all the different units that I've identified. So there are 3 possible instances of water, including at this truncated unit here, based on the observations that I've made. But nothing is that simple. So I talked about the 2D agreeing with the 3D, but not with other 2D to use these acronyms. But we were basically trusting that that draped image was agreeing with the 3D image below it. And it turns out that when you actually visualize these things in 3D and you're studying the boundaries of layers in detail because you're trying to get their inclination and thickness, suddenly it's not so nice. So you see here, there's sort of this dolly-esque draping of the image over these edges. And basically you can imagine that you have a cliff edge that's like pretty steep. And if the image is off by a few pixels, suddenly you have it draped over a different area. So it kind of looks like it's in the wrong place, like it's melting. So if I'm drawing all these boundaries and I'm getting quantitative data, I'm trying to get these angles, and the angles are pretty shallow. So any sort of change will tip it in the other direction. Can they be trusted? Can I say this is an unconformity, that this is an environment change, or was there just some pixel error there? And that's a huge problem. It's also a big result because we're not really doing a lot of work in this 3D outcrop analysis on Mars. We're doing loads on Earth. So this is really important. All of a sudden, sure, you have this high resolution data, but on a, say, 5 to 20 meter scale, you're seeing these offsets that can really mess up your quantitative look at what's going on in the history of the geology here. The imaging directly impacts the geological analysis. So there are a lot of lessons from that. I definitely argue that we need to train geologists to do their own image processing because it's really important. Whether you're aligning things or whether you're evaluating error or interpreting something and need to know how much you can really trust something that sort of looks like it's melting. I think that's really important. I think it will impact future landers and rovers as more and more people look at surfaces in 3D. The technology is also advancing. We're going further out into the solar system. So say we land somewhere where we don't have global ground truth, somewhere like Europa or Titan, these big moons of the outer solar system, where we're hopefully landing in the next 3 decades. That's going to be really important. It's going to concern hazard planning for engineers. It's going to concern the scientists who are looking at those data for the decades afterwards. Going back to the image processing, the automation is great until it isn't. It's not necessarily better. It just depends on who you are and what you're doing with it. And to address those things, I think we need a comprehensive understanding of how we actually think when we're using these virtual outcrops, because I'm going to think differently than a professor who's been working in the field for 30 years is going to think when they look at my imagery. We're going to think differently than an earth scientist who uses drone imagery and has done that for years with that technology that has existed here. So any sort of survey that's using drones in combination with satellites and seeing how geologists actually think about these things will really be important to actually the image processing, the computer science end of things. Finally, there's a recommendation from Catherine Stack-Morgan in various publications about, so we have all this regional science that's being developed, this sort of map that we're getting in a lot of different places on Mars. And we also have rovers, and rovers are pretty close to here. It's 30 kilometers away from Curiosity rover. And so I'd really like to expand this type of analysis to the entire region and also try to look at ground truth from the rovers and see what kind of iterative lessons we can make, whether the regional interpretation enlightens us about what the rover sees and what the really, really detailed high resolution but very local science from the rover can tell us about what we're actually seeing or misinterpreting from satellite data. So thank you so much for listening. And I have all these 3D visualizations and even more if you go to this QR code, just for more fun looking at planetary surfaces in 3D. And yeah, I look forward to hearing your thoughts and questions. So thank you.
Thank you so much, Divya. That was a really, really inspiring and just fantastic talk. I really, really enjoyed that. It's some amazing graphics. Do you have any questions from the audience? You can either unmute yourself or raise your hand.
Well, I guess I have a question. Thanks for the really very interesting talk. I used to work in image analysis, and it's always fascinated me. And are you familiar, by the way, with the story about the tapestry in New York at the cloisters? They took photographs of the tapestry. Well, first they laid it out on the floor, this ancient medieval tapestry about the hunt of the unicorn, which is a famous tapestry. They laid it out on the floor and they started taking pictures of it, very high resolution pictures, and they went over it, you know, like a satellite would go over a planet. And then they tried to restore the entire image by stitching together those separate pictures, and they found that they couldn't, because as the tapestry lay on the floor, it sort of relaxed in a way that, you know, if they'd hung it up and just took the things that way, they might have not even noticed. But as it lay on the floor, certain threads shrunk and other threads relaxed, and so when the image cut through a person's face on the tapestry, for instance, it was misaligned. So you, by your head shaking, I gather you've not heard that story of you know, over in the humanities, where the very same, well, some of the same issues, they're not 3D, of course, but some of the same bizarre effects of image analysis have come up. Well, I recognizing your injunction that you ought to do your image analysis yourself, what's the best tool or maybe set of tools that you should use to do that with? I mean, is there sort of a state of the art in these reconstructions, or should we all be working in Python or something? What do you suggest?
There's a lot of state of the art with making 3D imagery for doing photogrammetry. So I use a combination of state of the art and some in-house stuff, but basically in the planetary community, there are sort of two gold standards. One is an open source tool produced by the community from NASA Ames called the Ames Stereo Pipeline. And that's sort of dedicated to planetary imagery. And then the other one is Socket, which is produced by BAE Systems, and that's used loads on Earth imagery. So there are standards for processing, and a lot of what I looked at wasn't necessarily issues in processing, although I did a little bit in the thesis. I I think a lot of it ends up this conflict between how much intervention we want to have in the image processing. So with Socket, you have your stereo computer, and it's like projected in 3D in front of you, so you can actually draw the lines between pixels and make those match points for the algorithm to do, and you can refine it, which is really intensive. It is why we developed these automated methods, because it's really difficult. But then, as I show, these automated methods, you lose out on detail, and sort of depends what you want. So yeah, I think we have the state of the art. I think what we need is, and this is something that like the US Geological Survey is working on, how can we evaluate error in the models and combine the two, especially? Can you actually do some hand drawing and iterate between the automation? So I think that I'll leave that up to the computer scientists, but it's definitely a conversation I think is emerging in planetary science that needs to continue to emerge, because I think a lot of us as geologists sort of accept whatever products are given to us by our colleagues, or download from a website and just say, okay, this is the truth. But we really need to actually have some quantifiable error from these things, which is difficult to achieve. Yeah.
Well, so is your, I mean, your perspective seems to be that there's a truth out there, and given these resolutions, we should be able to discern it. But maybe, and maybe you said this, and I'm sort of half-brained about this, but you could also treat it like just naked uncertainty, as if it were imprecision that you measured directly. Is that what you're saying too? I mean, when you say quantify,
yeah, that's better said than I've been saying it. So thank you. Yeah, definitely. I think we can't treat it as truth, but we should be able to say what, at least be talking about the uncertainty, which
right.
yeah,
I resolve it, and with these interventions, these manual interventions that you suggest, if they can still end up with 20 meters difference, that's somebody should notice that, right?
Yeah, exactly. And it's very much a nascent methodology of using 3D outcrops to look at these data. Usually when we use 3D models, we actually look at them in 2D and just sort of sample, if that makes sense, in 2D mapping software. So this is something that's like very, very new that people have been doing probably the past 3 to 5 years. So it's understandable that we haven't run into any sort of publications like capturing these issues. So it's good to get this conversation going about what uncertainty is once you start looking at these things really close up in 3D as if it's truth. So yeah, I'm interested in seeing what other people are noticing.
Yeah. Well, thanks again for your talk. It was hard to ask questions because it was so exciting. My mind is sort of swimming in that.
Thanks so much.
Yeah, I have a slight question based on what you were just saying as well. I'm curious, like, how much is the cost saving and kind of labor saving from automating it? Like, what factor of kind of scale are we talking about here?
Yeah, it's kind of hard to conceive of. So processing a high-rise image in an automated way with the in-house software takes about a week. Doing it by hand would probably take several weeks. And the good thing is with automated, you can sort of batch process if you want to. I didn't really mention that. I don't think you should batch process, because I think you should really tailor parameters to what you're seeing and what you want to do. But if you want 100, say CTX, which are the 18 meter per pixel models, you can just throw it onto your advanced computer system and like let it run. And in a few weeks, you'll have hundreds. Whereas if you're sitting on a computer and it's doing this intensive, quite labor intensive work, and you just produce one model at a time, and they're different each time, it's quite difficult. So I've never actually done the manual version, but it's my understanding that it can take weeks, and you might have to go back and retry multiple times. So yeah, it's significant.
Yeah,
but
that's
also
huge.
Yeah.
Yeah, thanks. And another question I had actually is around when you're talking about kind of volcanic kind of morphology or geology, on Mars. I'm curious. I wasn't aware that there were any volcanoes on Mars. Are there any active volcanoes on Mars? And if there
There are no,
were,
yeah.
how would you go about modeling that?
Great question. So there aren't any active volcanoes on Mars. Well, I'll say there aren't technically. There are ancient, considered dead volcanoes on Mars. And some of the biggest volcanoes in the solar system are on Mars. The biggest mountain, or one of the top 3 biggest mountains in the solar system, is on Mars, and that's Olympus Mons. So way back in the day, there was really active volcanism that was similar to stratovolcanoes, sort of these domes, and also you get these smaller. I don't know exactly what size, but they're, it's Olympus Mons is massive, but these little domes that you see across the northern hemisphere that sort of look like mud volcanoes. So basically when you have a magma chamber interacting with groundwater and explodes, it's really energetic, and then you get loads of mud traveling really far distance. So Mars used to be really volcanically active. And the reason I say it's not technically now, I think it's the South Pole, you still get these like little explosions. And that's it's when you have CO2 and water ice in layers, and then it's exposed to the sun, and you get a little bit of melting, and then it suddenly sublimates and you get these explosions, which a lot of people won't say is volcanism, but when you look at icy moons, that is what volcanism is. So yeah, there's still explosions happening on Mars, which is pretty cool. In terms of modeling, I am not a volcanologist. I don't really know. I think a lot of it is comparing to places like Hawaii, places that have volcano systems that have been emplaced from when you get a hot spot. So there weren't tectonic plates on Mars, so the volcanism is a bit different. And it's thought that there were just these sort of magma plumes coming up from the mantle and feeding these volcanoes. So that's similar to what we see in Hawaii. So I know there's a lot of like field work going into understanding that type of thing, but very much outside my wheelhouse.
Yeah, no, thank you so much for sharing that. That's really, really intriguing. Do we have any other questions from the audience?
I'm curious about the, I'm sorry if you mentioned it, but about the automation method. It's like, do you use some sort of AI or something, or?
Yeah, so some people are increasingly using AI. The automation that I use, to summarize. So yeah, I'll give you a quick summary. NASA has produced a series of scripts that I think are in C called ISIS, and those are image processing scripts to do things like calibration and basically various things, anything you want, sort of on a first order. What, say, AIM stereo pipeline does is it is a wrapper for those commands, and then it combines a lot of them. So it has a stereo matching algorithm. It has different things. And stereo matching comes from, this is work that's been done for several decades in computer science of, it's based on not human eye optics. I think it's around cat eye optics, where it comes from optical science of how to match two images, and feature tracking and feature recognition actually goes back quite a long time, well before AI. And some of that goes into stereo matching, not so much as what I just said, but so there are a lot of these algorithms that have evolved over time. They've become a little more insensitive and also robust as computing has advanced to do this type of computing, but it's not AI. It's very much based in optical science. So AIM stereo pipeline has these little wrappers for these different commands of the NASA commands. And then on top of that, the in-house software basically bundles all of those AIM stereo pipeline commands to do like stereo matching and then outputting the DTM and refining it into just one command. So basically you edit a text file with the images that you want, and it just runs it. So there are a few different steps, but none of them use AI. And this is something that's definitely being worked on right now in a lot of different industries to improve it, because AI would just massively improve stereo matching because it is very intensive. So that's kind of a general summary. I would definitely recommend reading more about photogrammetry. It's very numerical. It tends to be sort of iterative. So you have like a little window that travels across both images and looks for matching pixels. It might look at densities. It depends on how you actually run it, and brightnesses of pixels as well. So yeah, I hope that makes sense.
Yeah, it makes sense. Thank you. So I guess your method doesn't suffer from the replication problem that AI, with AI, depending on the hyperparameters you take for your models, then you may have a different solution. So if you run this code in this computer and then you run this other code, this same code in a different computer, then you might have different results. But I guess with your method, you don't have that issue, right? Or do you have to give some input parameters?
Yes. Yeah. So as I said, the in-house software, you don't have to input as much, but you can input as much as you want. And those parameters will be things like so I said there's like a window that scans between the two images. You can change the size, the precision. The algorithms that actually uses are going to differ between different software. So that gets into computer science. It's a little over my head, but parameters like that you can change. You can change when you're doing refinement. You can apply secondary algorithms that, for example, look at density features. A lot of this has been the improvements from the in-house on top of the standard or the open source methodology has been applying these secondary algorithms that are better at pixel matching because they iterate around a radius. So two separate people processing the same image might have two different results. If they're using the same parameters, it won't be differences quite like what we see, I think, with AI in the same way, in that you can probably look. I actually I don't know. Maybe it is very similar. So yeah, I hope that makes sense. Basically, there's a lot of user input you can have. A lot of what the automation does is takes that out of your hands. Some of it does it intuitively, or it does it on a mass scale, or it uses these algorithms that sort of shortcut around you having to think about some of these refinements on a small scale in the image. So it will be different. It will be different for sure.
Yeah, okay, thank you.
Thanks, Enrique. Maybe one final question, if anyone has any. And if not, then let's call it here. So thank you so much, Divya, for your wonderful talk. That was really great. I know Marco thanked you in the talk as well, in the chat, sorry. And yeah, just been an absolute pleasure to have you. And
thank you so much for having me.
Yeah, no, it's been great. So I'll send you an email with a link to the talk when it's been uploaded. And yeah, stay in touch. Thanks so much.
I will. Yeah, thank you so much. Yeah,
All
take
right.
care.
Take care. Bye.
Bye.